So in the last video, we sort of introduced you to the idea of work and energy, more specifically kinetic energy, where if you do work on something, you apply force to something, it moves distance, you do work on it, you then can give that object kinetic energy. And we had sort of like the work is equal to the change in kinetic energy, and often referred to as the work energy theorem. Now you got to be a little bit careful using that sometimes because, you know, we've got the work. And of course, the work is equal to force times distance. Well, sometimes you'll have the cos theta at the end there. But we have the work equals FD is the main expression. And of course, this turns into kinetic energy. And of course, that was 1/2 mv squared. Now, you can be a little bit careful because with that force right there, this is often your net force that actually is used. So if you are pushing on something, you're applying a force to something, when you do the work, there might be friction. And often what happens is, you do work which is equal to FD, no problem, but it's often the net force that is actually used to give that kinetic energy. So let's sort of look at it this way. You do work on something, and work is equal to force times distance. And of course, this is however hard you are actually pushing on it. The applied force times the distance. And that's how much work you do. Now, some of that energy will go to kinetic energy, and that's fine. But if there's friction involved, some of that work goes against friction. So this actually can sort of get split up. And if there's a force of friction, the force of friction times that distance will take up some of that energy. And on the other hand, if we have like the net force times the distance, this is the part that goes towards kinetic energy. And this top part here, this is like lost to things like heat and sound and that type of stuff. So when you do work on something, not all of the work, not all the energy that you use goes towards moving the object. Not all of it goes to kinetic energy. It's typically the net force is the stuff that actually used or goes towards kinetic energy. The rest can be lost to heat and sound. Of course, there's other things can go to as well, but if you take those two works, if you do that FD, you calculate that, you do that FD, take that, and you add them up, you should end up with the work or the energy that you started with. So you got to be a little bit careful sometimes. A lot of the stuff is pretty simple that you guys do. You don't have to worry about it. But in reality, not all the energy that you use goes towards kinetic energy. Some will get sucked up by friction and stuff like that. Okay? All right, so we're going to look at a different aspect of doing work and a really, really common scenario or form of work that is used all the time. And we're going to use a little picture here to help us out. There we go. Okay, so we're going to use this guy over here. Okay, so here we've got a little creepy little green kid, and we got a slide. And of course, the little guy here, he wants to go on the slide. So what does he do? Of course, he climbs up the ladder, and then of course he comes sliding down. Okay, obviously that's what you're going to do. Now, in order for the little guy to actually slide, he needs to climb up. And when he climbs up like this, he is applying a force and he's doing or traveling a distance, which means he's doing work in order to get up the slide. Now, the thing is, when he's down here, he's at rest. He's got no kinetic energy. He does work to travel that distance, and then he's standing at the top. But he's just at rest still, so he still doesn't have kinetic energy. So that work that he does must go towards something else. And that's what we're going to look at a little bit today. So actually, I'm going to move this over just a little bit more. So we take this little guy, and when he goes up like this, okay, when he climbs up to the top of the slide, he does work in order to travel up. Okay. Now, of course, when you do work is equal to force times distance. Now, how much force is he using to get to the top of the ladder? Well, at the bottom here, I mean, he's got to, use his little, I assume he's got little legs underneath his little close, he has to use his legs to battle the force of gravity to get up here. And since he starts at rest and he ends at rest, his overall force that he uses is going to be equal to the force of gravity. Now, obviously, to get going, he's using more than gravity. When he slows down, he's using less than gravity. But the overall average force that he uses must be equal to the force of gravity, and that's why he can start at rest and end at rest. So the amount of work that he does, this has to be the force of gravity. So it's like his average force has to be equal to the force of gravity. And the distance that he travels, it's a vertical distance, and typically, just like we did projectiles, vertical distance we often just refer to as height to like distinguish it from other things. So the work that he did would be then equal to the force of gravity times h. Now, of course, the force of gravity would just be equal to his weight, which of course is mg. So I've put that in there. I guess it looks like this. It's got mgh. And this is how much work he does in order to climb up the slide. Now, this did not go to kinetic energy because he's not moving, right? So where did that energy go? Well, the energy is actually stored within him, and so you probably figured out this is stored as what is called potential energy. So this is how we can calculate potential energy. Now, more specifically, this is gravitational potential energy, which is a very, 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 very common form of potential energy because things are lifted up, things fall down all the time. All right. So when he goes up to the top of the slide, okay, so he's down here, he does work against gravity to climb on up. He gets to the top, and he's got all this potential energy inside of him. And then what does he do? Well, he goes down the slide. And as he goes down the slide, he goes back down to where he was before. Now, since his height is now 0 again, he has lost all of his potential energy. So he's got the most potential energy up here, and then as he slows down, since his heights get smaller and smaller and smaller and smaller and smaller, his potential energy keeps on getting smaller as well. And of course, when he shoots off the bottom here, he's going really fast. When he shoots right off like that. So he's going really fast, which means he has kinetic energy. So at the top here, he's got potential energy. And at the bottom here, he's got kinetic energy. And the potential energy at the top actually turns into kinetic energy as he goes down. And the two would actually be equivalent. So whatever potential at the top you have is going to be equal to the kinetic at the bottom. And that's the idea behind gravitational potential energy and its connection to kinetic energy. Okay, so we've got this gravitational potential energy when he's at the top. And we'll sort of label it on here. So here at the top, he has potential energy. I just like to call it the EP. So he's got potential energy there at the very, very top. And at the bottom here, of course, he fires down and he's shooting really fast down there. Down here, he has kinetic energy. So he's got potential energy at the top, he's got kinetic energy at the bottom, and one sort of turns into the other. And in between, at any point in between, since he's still off the ground, he still has potential energy, but he's also moving, so he has kinetic energy. So in between here, he's got a combination of both. He's got potential energy as well as kinetic energy. So we start with potential at the top. As he goes down, it turns into kinetic energy, and anywhere in between, you're going to have a combination of those two put together. Now, it doesn't matter where you go. You can start at the top here, you can be at the bottom here, or here. Ideally speaking, if we take all three of these, and we talk like in a perfect situation, okay, if this is a perfect situation, all three of those are going to be equal to each other. So potential in the top, kinetic at the bottom, and one turns into the other. And this isn't a perfect situation, okay, with no friction, nothing like that. So it's all good. Now, this is what's called the conservation of mechanical energy. That's what's often referred to. So we have what's called the conservation of mechanical energy. And it's a really, really simple idea. Basically, your potential and kinetic at one place is going to be equal to the potential and kinetic at another place. So you'll often see something like, potential energy 1 plus kinetic energy 1 is going to be equal to potential energy 2 plus kinetic energy 2, something like that. So basically, the sum of the two energies at any two locations should be the same. It's often referred to as the conservation of mechanical energy. Now, the nice thing is if you know the total energy at one place, like you know its potential or you know its kinetic, you then know the total energy anywhere in the situation. It doesn't really make much of a difference. Okay, so let's sort of show you how this works and how this all can piece together, and we will work with it a little bit. So I'm going to see if I can get this out of here. We're going to copy paste. All right, excellent. Okay, so I'm going to do another little version down here so I can get a little more room. I'm just going to make it a little bit smaller. Here's that. See if that'll work. Oh, it did work. Excellent. Okay, so we're going to have this guy over here, and let's start him with up here like this. Okay, so let's make up some values here. Let's say, well, he's not very big, so let's say he is 30 kilograms seems like quite a bit for that little guy. Let's change it to, let's say he's just 12 kilograms. All right, so a little 12 kilogram guy, and he went up the ladder, okay, and at the very, very top ladder, so let's say he went 4.5 meters. Okay, so let's just start really, really simple. So let's just start with his potential energy. What is his potential energy at the top? So his gravitational EP is just going to be equal to mgh. So I've got his mass, I've got his, I know the acceleration due to gravity, and I can find his height. So 4.5 times 9.81 times 12. We put those together, we're looking at around 530 joules of potential energy. And that's all he has at the top. Now, the nice thing is, as he goes down, it all turns into kinetic energy. So I know at the bottom here, his EK at the bottom is also going to be 530 joules, something like that. Okay, so if I know what his kinetic energy then at the bottom, I could even find out what his final speed is, because this is going to be equal to 1/2 mv squared. So I can find out his final speed. So if I take that energy and I times by 2 and divide it by his mass, and then square root it, I can find out at the very bottom, he's going around 9.4 meters per second. So he's cooking pretty good. But I can also go in between. So maybe what I want to know is, what is his speed when he is, let's go 3 meters down. So maybe like right on. So maybe he's gone down 3 meters. And how fast is he going when he's about 3 meters down? Well, we can piece things together here. Well, first of all, there's a couple ways you can actually do this, and it doesn't really matter. But I could find his potential energy at that location. And if he's gone down 3 meters, then his height would be 1.5, because he'd still be 1.5 meters off the ground. So if I do the mgh and I use a height of 1.5 meters, I can see that his potential energy would then be around 177 joules. Now I know his total energy has to be 530 no matter what. Top, bottom, it doesn't make a difference. Now if out of that 530, right now his potential energy is 177, which means the rest has to be kinetic energy. So I just got to subtract the two. So therefore his EK has to be equal to 353 joules. So those two energies will then add up to 530. So now I know how much kinetic energy has gone after going down 3 meters. And there's a couple different ways you can do this, but this is the classic energy way to do it. So now if I do this, if I make that equal to the 1/2 mv squared, I can find out his speed at that location. I already know it's going to be less than 9.4, but I can find out how fast he's going after that 3 meters. And when I punch it out, I get around 7.7 meters per second, which seems about right. Okay, and that's basically how the conservation of mechanical energy works. Now, notice that like it's a slide, it's an angle, it's an inclined plane. We didn't mention anything about the angle. We didn't measure like the angle of the slide, the angle is coming, because one of the great things about using energies is they are scalar quantities. They don't care about direction, they don't care about angles, they don't care about any of that stuff. It's all about how much potential do you have, how much kinetic do you have, is one changing into the other, and they add up to the same amount. And all of it comes out of basically work equals FD. And that is how the basic conservation of mechanical energy works. And energy is a great way to work with basic mechanics type questions, especially when things are going up and down. Sideways, you can do it as well, but especially when things are going up and down or moving because of gravity,